Hello, I'm Rob Hollow. I'm Education Manager at CSIRO Space and Astronomy in Australia and also Chair of the NAEC for Australia. So today I'd like to share some ways in which you can introduce students to concepts of radio astronomy and use data in a range of activities. So we're talking here about utilising the radio part of the electromagnetic spectrum, the long wavelength, low frequency, low energy component. And with the data we're talking about, one of the advantages we have is there's lots of it, and there's a lot more coming with all our new telescopes. Much of this is freely available in public archives online. Radio waves are not affected by day or night, so we can observe day or night. And in fact, there's ways now that you can build a simple radio telescope to operate within a school. But there are some disadvantages with the data. It's less obvious than optical. We don't, see things with our eyes. With radio waves, the images and data can be harder to engage with just through lack of familiarity. File formats can pose problems to the uninitiated. The tools mostly still are those for professional astronomers and are Unix-based, and that can pose challenges. And we can have extremely large file sizes. But here we can see examples of both an intensity plot and a plot of a supernova remnant as an image from two of our radio telescopes here in Australia. I like to introduce radio astronomy to students of any age really by using a transistor radio. You can pick up static, you use it to search for sources of interference such as a laptop screen, electrical cabling, power points and the like. So you can relate it to environmental education and talk about the transistor as a radio telescope with an antenna, circuitry and with an output, in this case a speaker. Another simple activity would involve colouring in intensity plots. So here we've got a Sardinia radio telescope has done a scan and produced a plot, and students can colour it in. So this is from INAF, and there's more sort of involved examples where you can use coding to analyse an image and assign colour palettes. Another traditional approach, of course, is with worksheets, and here we've got some great examples from ICRA in Western Australia, and they've developed ones for different levels using radio data to weigh galaxies. Another way to approach this is through sky tours. You can visit observatories virtually, and we can view the sky at different wavelengths using browser-based tools. So ALMA have developed the Google Street View walkthroughs of the ALMA sites in northern Chile that are normally inaccessible for most people. And we'll see more of these sorts of things in virtual reality and augmented reality over coming years. We have an online browser-based virtual tour of the Murchison Radio Astronomy Observatory in Western Australia, which will also be the home of the SKA LO in the next few years. GLEAM was an all-sky survey using the Murchison Wide Field Array at low frequency from the MRO, and here it fits on the chromoscope backend to allow you to easily look at the sky and compare at different wavelengths, and you can zoom in. Our Rapid All-Sky Continuum survey done with ASCAP is also available as a virtual sky tour, and you can click on the highlighted regions here, for instance, and get a close-up of what that image looks like. A more interactive one actually is the EMU Pilot Survey, Evolutionary Map of the Universe, the new ASCAP survey, and it uses the Aladdin Sky Atlas, so the professional database and storage and interfaces, and you can click on from the left and zoom in and see something such as this active radio galaxy. Another great approach is using citizen science. Zooniverse has had several radio astronomy projects up. The current version of Radio Galaxy Zoo uses data from LOFAR to look for AGNs, and Bursts from Space uses data from the CHIME telescope in Canada to look for fast radio bursts. And again, these require no installation, they're very flexible and very engaging, and students are actually contributing to real science there. You can build and use small radio telescopes. Radio Jove has been around for quite a while now and use dipoles, low frequency. We can use satellite dishes, a small one such as the itty bitty telescope, or a slightly larger one here, the ICRA built, and you can see a student showing the effects of putting their hand on the source and seeing the effect there. And with this sort of thing, you detect the galactic plane and can do other observations. I think a real game changer, though, has been these software-defined radios. The sort of dongle here of the order of about $50. You can use with just a standard radio antenna and computer to map interference and radio stations, or you can build an actual radio telescope quite simply, and for under $200, you can have a complete package. And here's one we developed for schools. We want to trial it once COVID lockdowns end here. It actually uses cardboard and aluminium foil and a paint can for the waveguide. And here you can see some data where it's calibrated for H1 line. And these are really good because they're not that expensive and they really do encourage experimentation with students. So it's a real hands-on type approach. There's the technical side of building it, calibrating it, and then just tinkering and trying different shapes of waveguides and the like. There's lots of, there are a lot of programs using professional facilities, or growing number. Long-standing one has been the Pulsar Search Collaboratory here in Greenbank in America, using data to search for pulsars. Goldston Apple Valley Radio Telescope uses an XDSN dish and has a wealth of educational resources, online observing for projects such as SETI, Jupiter, active galaxies and the like. INAF have developed a program where they use data from the Sardinia Radio Telescope to look for FRBs, or fast radio bursts. You can see some data here, and an English version of this activity is currently being developed. The Victorian Space Science Education Centre in Victoria has set up in a remote site in rural Victoria a off-the-shelf 3-metre spider telescope that can be controlled fully remotely. Schools across the state can book in, use it during the daytime, make observations and data analysis, and it comes with a complete range of curriculum support and project and Moodle. And it's a really effective, relatively affordable program. For many years now, we've been running this Pulse at Parks program here at CSIRO using the iconic 64-metre radio telescope. Students control it remotely live in real time, study and observe pulsars, analyse their data, and get to interact with our astronomers and our PhD students. Online module allows them to analyse the data, determine the dispersion measure of a pulsar, and then fit it to a location on the galaxy and plot multiple pulsars and see their distribution across the galaxy. A more advanced version of allowing us to do other science is under development using Jupyter Notebook. So again, fully online, and we'll expand the type of science we can do. So we can see here, for instance, H1 emission from the data from this test, and we hope to roll this out very soon. And radio astronomy data can be used for student investigations. Had a number of students use it at the top level. This is the Science Extension course in New South Wales. Student used archive data from RACS, the Pulsar catalogue and LADDN to look for an association between very young neutron stars and supernova remnants. Here's some of her analysis. And so simply using readily available online tools was able to come up with some very interesting results. And I think there's a lot of scope to develop this. So radio astronomy works at many different levels with students, be it browser, archive data, building and operating a telescope, or using professional facilities. We would like better tools and more, I guess, educationally appropriate tools for students. And there's going to be massive data sets coming, telescopes such as ASCAP and the Square Kilometre Array. So if you have an idea or are interested in this, we'd love to chat with you. Thank my team and colleagues at ICRA and INAF for their contributions. And thank you very much.